Can you all hear me okay? Yeah, it's almost 40 years since I've known Sean, and so that's a long time. When we first came to Dallas, I started working for ARCO. He had just a few years earlier come here to work for Mobile, and our another friend Jed and Sean, they worked at Mobile together. He got his Ph.D. at University of Kentucky. His wife is not here, but they have been together now for a pretty long time as well. I asked him especially what he would like me to talk about among his accomplishments, and he wanted me to mention two things. This year, he got a distinguished alumni award from University of Kentucky for his accomplishments in the field of geology.
It's Tennessee.
University of Tennessee, and the other award he got this year was from the Federation of Tamil Federation of Tamil Sangams, which is a Tamil federation. Actually, the Tamil diaspora from India itself is a pretty large diaspora outside of India, in Sri Lanka, all over the Far East and parts of South America. So you got the award actually in Atlanta, didn't you?
No,
you was right here. So these two have. The other thing about Sean's work is about 20 years ago he got interested in work done by my advisor at Columbia University, John Sanders. John Sanders had published in the 60s and early 70s papers on turbidites and trying to distinguish that not everything is turbidite, even though Obama sequence had come in the literature and everybody was calling, if you see a turbidite Obama sequence, it's the Obama sequence of turbidite. And Sean picked up on that, and he has written a lot since then, expanding that work, but the irony is that Sean never met John Sanders.
That's right.
But he has followed that work, so he and I essentially learned from the same professor, even though he never met that professor. With that, I will turn over to the work that he has done following some of the present-day plumes all over the world.
Thank you, Naresh. I am from a state called Tamil Nadu in India, so I'm going to greet you in Tamil. Vanakkam means greetings and good evening. First of all, I want to thank Dallas Geological Society for giving me this rare opportunity. When I say rare, I meant it, because I came to Dallas in 1978, and it has been 40 years. During these 40 years, I was invited 4 times by the Dallas Geological Society. So it's one every 10 years. So my next talk at DGS will be 2028. But don't worry, I won't be here. Probably I'll be reincarnated as a mountain goat in the Himalayas. Although I'll be a goat, I'll be close to the rocks, so I'll be doing geology. The other good news, as a goat, it'll be very difficult to publish papers. So that's a good news for you. So it's a win-win situation. About two months ago, Gloria Eisenstadt, the chairman of this group, sent me an email saying, would you be interested in giving a talk? I said yes. And she said, send me a title and the abstract. I sent the title and the abstract. That title is quite different than this one. And she said, in order to attract people to come to this dinner, let's put in some catchphrases like the Turbidite fans models. So we did. I didn't have any problem because that is essentially the conclusion of the talk I was going to give. So she announced this title, and after that that was early September. Then late September, I went to Tennessee to receive the award. I gave the same talk there. When I came back to Dallas, I was checking out all the slides are in the right order for this event. I noticed a problem. The title says Turbidite fan models, but in the selection of slides, I had only one slide talks about turbidite fan models. That means probably less than a minute. Suppose if one of you bought the ticket to come to this dinner thinking I'm going to talk about turbidite fan models, that'll be disappointing. So what I have done is the first part of this talk as a review of turbidite fans, some of the controversies, then I'll go on to the originally planned talk on density plumes and so on. And in doing that, I'm also going to narrate the growth of Mobil Oil Corporation, for which I worked for my entire professional life. Because what happened to the growth of the Mobil Corporation directly impacted the research and the personnel. So it's all integrated in one way or another. So with that introduction, let me begin. If you don't mind, I'll sit down. This is the first place I worked. It was located in Duncanville. It was called Field Research Laboratory. And as you can see, that's the main entrance. That's the main building. Behind that, there are a lot of smaller buildings. The one is the geochemistry unit. So when you go there, it's like a military barracks, a lot of little buildings put together. It was very basic, but functional. So that was the environment I joined Mobil. At that time, we stayed in the building from 78 to 83. Only 2 people worked on that program. That's the project leader, Dick Maiola, and myself. One of the things we did was we just planning the program. It was a very limited budget. So that's how I started. And these are the people who worked at the time in that building. The next year, 1979, the great Iranian Revolution took place. The Grand Ayatollah Khomeini was in exile in Paris, and he was coming back to Tehran in Iran as part of the revolution. And they packed the Shah of Iran into exile. The government was dissolved, and they stopped oil production completely. So as a result, what happened? The oil price went from $20 a barrel to $40 a barrel in a matter of just 12 months. Are you able to hear now? The mic working? Huh?
Yeah, it is there. Just hold it like this. So it should
Oh, okay. Is it okay?
Just hold it right below your lip.
Is it okay now?
Yeah.
Yeah, okay. Thank you. So the oil price went from $20 to $40. As a result, the price of gasoline went up. The American audience started blaming the big oil companies. So all the big oil like Exxon, Mobil, they all got that bad rap on this thing. Then comes the chairman of Mobil. This is Mr. Raleigh Warner Jr. And he joined Mobil in 1953. And Soconi, at that time it was called Soconi, that is the Standard Oil of New York, Oil Company of New York. He quickly moved up the rank. In 65, he became the president. 69 as the chairman. During that period, he transformed Mobil from an average oil company into the world's second largest company, American company. The way he did it was, he started increase the production in Canadian Atlantic, in the Gulf of Mexico, in North Sea. More importantly, he raised the stakes in Saudi Arabia. Mobil built one of the largest construction projects, that East-West pipeline in Saudi Arabia. 2 years later, they built the world's largest refinery in Yanbu on the west coast, along the shores of the Red Sea. Plus, Mobil was very instrumental in teaching courses for Saudi Aramco. As a part of that program, I went there 3 times, started teaching 3 times. The last one was in 1990. That was the year we had the Gulf War. I had an encounter with the US Army. That was an interesting story, but I would like to tell the story at the end of this talk during the question and answer session. Then he also changed the logo from just simple Pegasus to Word logo. Perhaps the biggest thing he did was sponsoring Masterpiece Theater on public television. He didn't just give the money and told them to go do it. He actually suggested programming. He asked them to bring Upstairs, Downstairs from England. That was a very popular series in England. When they started showing in this country, American audience loved it. And ever since, the Masterpiece Theater became a classic program on PBS, and it did change the image of Mobil from a bad company to a good company. And also Mobil started making a lot of revenues. At the time, Mobil wanted to build a new research center because the Duncanville facility I showed you, it was a very moderate military barracks type looking. So immediately, Mr. Warner and his wife got involved, and they selected I.M. Pei as the architect. Who is I.M. Pei? He was selected by Jacqueline Kennedy to build the Kennedy Memorial Library in Boston. Overnight, he became very famous. He also designed and built our Dallas City Hall, the Meyerson Symphony Hall in Dallas, and he's best known for this glass pyramid in front of the Louvre Museum in Paris. When you go there, it's one of the most magnificent structures. When I first saw this building, I exhausted 3 rolls of films. Each roll had 36 shots. So you can imagine how much I liked that building. So he designed this building. This is on Alpha Road, and I think currently it's occupied by a school, a parish Episcopal school or something. Anyway, this is the inside foyer. It's a very fancy building, and Mrs. Warner thought this place should not be just a place for work. It should be a place for enjoyment, art, culture. So there were big murals was hanging on the wall and so on. Most importantly, this is the best time for our turbidite research in Mobil's history. And what happened was they increased the funding for research. They also started hiring new people. The 2 new people, the red dots I put in there, one is Jed Damon. He's in the audience. He was at Lamont Doherty Geological Observatory of Columbia University. when I went there to look at some contourite cores, he was interested whether his mobile is hiring. And that was good news for me, and because I always wanted to have a person who looks at modern marine systems that will help our research on the ancient deepwater deposits. So he joined Mobile. The other person is John McPherson. He used to be a faculty member at UT Arlington. He's originally from New Zealand, and I also encouraged him to join, and he did. And now he retired, now he's in Australia. And I listed some of the other people just to show the type of talents Mobile hired. For example, Roger Black from Stanford. And if you look at here, people from Harvard, MIT, Caltech, Johns Hopkins. This is one of the best bunch of people one could hire in an oil company. So that was the time. Even the interns, one year I had 2 interns, one from Leeds University in England, one from Stanford. Working for an oil company, having 2 interns in one summer from these top schools is just unimaginable. Going to work there every day, I felt like I'm going to a university research center. I never felt that I'm going to work for an oil company. The environment was so stimulating, and we used to get into all kind of arguments on the scientific level. It is probably one of the best places at the time to work for. Then the downturn. Mobile Oil started laying people off. I worked in this building from 92 to 2000. This is the final stage of deepwater research. And Mobile merged with Exxon in 99 and become Exxon Mobil. And they did offer me a job in Houston in the research. I politely declined. I stayed in Dallas. That is my office in the building. I listed these places when I worked there. We had probably the best collection of talents in terms of technologies and staff. So I would request you to join me in paying this tribute to Mobile people. I'm not borrowing up Mobile because the company doesn't exist. So it's purely a personal wish. This is probably the best place in terms of an oil company. Just to give you an example, I highlighted the person Mark Lindsay. He used to work in the graphics department. I used to take geologic models to him. He will make it come alive. I'll just to show you one example. I showed him what turbidity currents are, what contour currents are. I made a sketch very much like this, and he put this 3D effect showing as if you are standing on the seafloor, how the turbidity current will come and hit you. That's the kind of talented people we had at Mobile. And this was published in the AAPG Bulletin, and the SCPM liked the picture so much, they republished it on the cover of one of their special publications. I myself have hobbies. One of them is charcoal drawing, and this was done in 1972. And I also did some nudes. There are children here. And the APG Bulletin have published 6 of my photographs. I'm into photography. This one is taken near Chennai in India. There is a person sitting here. That shows this is a granitic monolith because of the erosion and weathering, it took this odd shape. The other picture published on the AAPG is the Praecastolan. It's called Pulpit Rock. Reaching there is rather difficult because you have to take a ferry from Stavanger to your little town. Then you drive for about 30 minutes. You reach the base of this rock. Then you climb up. That takes about 3 hours of hiking. It's a very steep terrain. Then you reach, there's a human being here. The whole thing is a glacial deposit formed about 14,000 years ago. The very sharp face is because the rocks are peeling off along the fracture zones. And if you watch movies, this year there is a movie called Fallout as part of the Mission Impossible series. And the final climax scene was shot here in this Pulpit Rock. And Tom Cruise was hanging out about that place. This is Cotopaxi volcano in Ecuador, and this is also very treacherous climbing. 2 weeks before we climbed, there were about 12 people got buried by avalanche because this glacier got melted because of the slight activities, and they got buried. And also the slope itself is volcanic ash and lahar, so it's a very slippery slope. Then when Geological Society of America was seeing all this, and they invited me to submit photographs for this special volume called The Art of Geology. This is one of the 4 photographs they published. And the Geotimes called, I submitted this, they published this one. Now back to the talk. The talk I'm going to give on this turbidites and fans, that's not based on some reading a few articles here and there and giving you a summary. This one is based on description of rocks, core and outcrop from 74 to 2011. It includes 35 case studies, 32 reservoirs, and it was described at 1 to 20 scale. And I have described over 11,000 meters of rocks, and over 250 people worked on this project over the years. One of them is in the audience, Jed Damon. He and I went to London, Aberdeen, Glasgow, Edinburgh, and we described cores from North Sea and places like that. So this is very rock-based talk. And also we went to, this is Dick Mayola, my project leader. We went to Spain to look at the classic submarine fans sequences that was studied by Professor Muti, and he was the consultant for Mobile at the time. He took us there. The very first thing I got into argument with Muti was, he was using the terminology turbidite rather loosely. Whereas John Sanders, that Naresh mentioned, according to Sanders, you can call a rock a turbidite only if it is deposited by turbidical. If it is deposited by various other processes, they are not turbidites. For example, if it is deposited by debris flows, you call them as debrite, not turbidite. But Moti was using this term very loosely, and there are other people, to them just turbidite means just a rock. It doesn't mean anything. So it drove me crazy because I went to school in India to this place called IIT Bombay, that stands for Indian Institute of Technology. This is one of the top schools for engineering and science and technology and so on. Some of the required courses there is soil mechanics, fluid mechanics, engineering geology, field courses, field projects on mass transport deposits, that is slides, debris flows, because every July and August, because of the monsoon flooding, major collapse of buildings, landslides, we used to go there and measure properties of soils to understand the mechanisms and so on. because of the background, I ended up arguing with Muti all the time. When it comes to the deep water sedimentation, I cherish the works of these people, these 5 people. First, Bagnall. He was a British engineer. He was the first one to define precisely what a turbidity current was. He said it is a Newtonian flow, it's turbulent state, and in which the concentration is always less than 9% by volume. John Sanders, that Naresh mentioned, is the other guy who followed Bagnall and said we should always use fluid mechanics if we want to define turbidity currents or other processes. George Klein, who was a student of Sanders at Yale, and he was the first one to introduce the concept of tidalites in deep water sedimentation. Of course, in the audience, Naresh Kumar, he got his Ph.D. from Columbia, and he was a student of Sanders. And Sanders moved from Yale to Columbia, and that's where Naresh got his Ph.D. So when Naresh told me that he's going to introduce me, I was thrilled because Sanders' student introducing me, I consider Sanders as my god as far as sedimentology is concerned. So I was very thrilled. And the other person is Shepard. He measured tidal currents in submarine canyons. Charlie Hollister, he introduced the concept of contourings. The reason these things are important because these are completely different processes. They are not turbidity currents. So before we go into it, I set some basic concepts in place so that there won't be any confusion, at least in this talk. Soil mechanics, they have this limit equilibrium analysis. They use the factor of safety, that is F, which is essentially the shear strength of soil to the shear stress of equilibrium. If the factor F is greater than 1 or equal to, then the slope is stable, nothing happens. If the stress increases more than the strength, then the F becomes less than 1, then the body begins to move. This is what called sliding. And there is no size, velocity, distance of transport, grain size, sea level connotation. This can happen just in a matter of a second if there is an earthquake. The other thing is rheology, which is the stress-strain relationship. If you apply stress to your fluid, if it begins to deform, it's a Newtonian fluid. On the other hand, if nothing happens until this point reached, then the fluid deforms. It's called Bingham plastic. This is turbidity currents. This is debris flows. And this also turbulent in state. This is laminar in state. So, using all the basic principles, we published a paper in the AAPG bulletin saying there is slide, slump, debris flow, and turbidity currents. All these three are also called mass transport. The reason they are the one that really transport sediment into the deep sea. Turbidity currents is not that important. Just to make this complex issue a little bit easier, I want to compare human transport to sediment transport. If you are in London, you take this double-decker bus. It can carry 73 people at a time. If you are in Sweden, you take this microcar, it can carry only 2 people. So that is what turbidity currents are. That's what mass transport deposits are. So when you talk about deep water sedimentation, this is more important than this. In addition, we wanted to find out some of the basic differences between debris flow and turbidity currents. So Mobile funded the civil engineering department at the University of Minnesota. It's called St. Anthony Falls Laboratory. This city in the background is the Minneapolis. That is the Mississippi River. This is the outside flume. They have a huge flume inside. We wanted to find out, can we generate sandy debris flows? Because the old idea was debris flows are muddy. So we did generate sandy debris flows. For example, when you introduce the slurry into the flume, all the sand is at the bottom. This move as a laminar flow, a plastic mode, so therefore it is debris flow. But finer material get into suspension, they move in turbulent suspension. They behave as a turbidity current. So there are two distinct processes. One is turbidity current, finer grain, debris flow, coarser grain. 10 years earlier, Postma published this diagram. They conducted similar experiments. They arrived at the same results: basal debris flow and upper turbidity current. The only difference was they called it high density turbidity current. The problem is the basal part is not a turbidity current, it's a debris flow. So if we talk to Sanders, he would strongly disagree with this terminology, lumping turbidity currents and debris flows. In fact, Sanders wrote a paper why this is wrong. And when you look at the modern submarine canyons, there are large boulders going in sandy matrix. These are sandy debris. But it was published in '66. People in the oil companies particularly didn't pay attention to this oceanographic documentation on marine geology because they thought it's some kind of oddball photograph. But in fact, this documents modern sandy debris flows. To show you how a turbidity current looked like, this is the turbidity current flowing towards you, and this fits exactly what Bagnall said in the beginning. It's Newtonian, turbulent, and is less than 9% by volume. When you put more sand into it, the whole thing collapses. It doesn't exist. That means coarse, sandy turbidity currents and conglomeratic turbidity currents, they don't exist. So when this thing deposits, they form a nice normal grading. That's what we call turbidite. So there are turbidites, and they do exist. This is how they look like, and I explained to you the physics of turbidity current.